In this video, I want to talk about the Bohr's model and also Lewis structures and how they are very important to help us understand how atoms or elements react with another, how they're reactive, why they react, who they react with, and what kind of bonds they make. So about a month ago, we looked at a neon light, but instead of neon, it was a hydrogen inside, and it was kind of a reddish glow. This one kind of looks purple, but it's kind of a reddish glow. And when we looked through a spectrometer, we actually saw that it diffused light in different colors. So here is eventually what Bohr determined. So he thought it was kind of weird that it only had specific lights. And what happened was that he understood it as shells. So these electrons are around. These electrons originally started, let's say, here. And if you gave it enough energy, it could jump to a level. And as it came back down that level, it's going to emit a light. So this one would be the blue one, and I get pink for the next one. So if the electron from here only jumped one level, and then as it goes back, it only emit a certain color. And then if you gave it even more energy, from here it jumped all the way out to here, as it fell back, it's going to emit different colors of light. Because of this, he was able to determine, like, hey, there must be a reason that they always go to these specific levels, and it must be that electrons occupy only in these specific shells. And this model is kind of important of how we understand atoms itself. You have a nucleus with protons and neutrons, and then you have these levels of electrons. So you have 2 electrons in the first shell, 8, 8, 8, continue on. When we get to the 4th shell, it actually gets more complicated because we're going to throw in d orbitals. But for now, let's just think 2, 8, 8, 8. Now, that led us to the Lewis structures. So let me get rid of these pictures and bring up the Lewis structures. So if we looked at Bohr's model with different elements, let me see if I could drag this over. So here I have oxygen on the left and sulfur on the right. You'll notice that they are different. So for oxygen, it has 8 protons and neutrons. That means it's going to have 1, 2, 3, 4, 5, 6, 7, 8 electrons on the outside if it's going to be neutral. For sulfur, it's 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So they are different elements, but when you look at it, the first shell, they both have 2. The next shell, sulfur has 8, but oxygen has 6. But then on the outermost shell for sulfur, it also has 6. Now, when it comes to reactivity, the outermost shell is the one that's going to actually react because it's on the outer one. It's the part that it's going to bump into other elements or bump into, whatever. And because it's the outermost, those are the electrons that are actually going to be reactive. The electrons within, so these electrons within, isn't going to ever see anything. So they really don't do any interaction. It's these outer electrons that do all the interaction. And since both oxygen and sulfur, even though they have different numbers of electrons, because their outer shell looks very similar, they both have 6 electrons, they're going to react very similarly. Now, sulfur is going to be a little bit different because these electrons are a little bit further away compared to oxygen, but they're going to react similarly to each other. So if we kind of just do that as a whole, and we looked at the Lewis structure here, so you'll notice that everything in the first column is going to look the same. So hydrogen, lithium, sodium, potassium are all going to have 1 dot because their outermost electrons are going to be the same thing. Same thing with our second row. Their outermost electron is going to be 2, then 3, then 4, 5, 6, 7, and then finally our noble gases, which will be 8. So that's kind of how it is. And that's why Lewis structures are helpful, because we're only focusing on the outermost electrons, the ones that are going to do the interaction. These outermost electrons have certain properties, so that's why I'm going to pull in the periodic trend here. So the main 2 that are pretty much the most important for us is going to be, let's see if I can find it, electron affinity. This one right here. Technically, you could just draw it like this, and that is electron electronegativity. So what does that mean? That means the desire for electron. Right here, we're missing francium. Francium will be down here. These guys, since it has 1, remember, they all kind of want to look at noble gases, so they want a full outer shell. Now, if they want a full outer shell, they have to either gain 1, 2, 3, 4, 5, 6, 7 electrons or lose 1. So even though they'd rather be neutral, losing 1 for these guys isn't a big deal. Now for fluorine, it's so close to neon. All it needs is 1 more electron right there, and it's there. So here, even they're really close, so there's really little chance that fluorine is going to give up electron when it's so close to neon. So fluorine really wants electrons, so that's why its electronegativity is the highest up here. And francium doesn't really care, because not only is it only 1 lone pair, but it's the 1, 2, 3, 4, 5, 6, 7th shell for francium. So it really barely, let's see, 1, 2, 3, 4, 5, 6, 7. So it's way out here, this electron. So if you take it from francium, you know, rather be neutral, but at the same time, it has a full octet. That electron's way out there, can barely even tell. So electron affinity or electronegativity is important. Ionization energy is very similar to it. It just means how hard is it to make it an ion. Since it's really easy to get rid of electron here, it doesn't mind. For fluorine, it really does not want to get rid of its ion. So it's going to be much, much, much more energy to do it. The next one is atomic radius. It's going to get smaller or bigger this way and bigger down. Down makes sense mentally, because as you're adding more shells of electrons, they're going to get bigger and bigger. Going this way is going to get bigger, kind of is counterintuitive because you're adding more electrons. But what happens is as you add more electrons going to the right, you're also adding more protons. So as you're adding more protons, it's going to attract those electrons closer and closer. So lithium's going to be slightly bigger, then it's going to get smaller, 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 smallest. Then it's going to go back big again to sodium, and then smaller, smaller, smaller. So each of these are going to be bigger, each of these are going to be smaller, and it's kind of that kind of trend. So because of these electron affinity, we're going to be able to figure out how these things are going to react. And the last picture I want to show is this one. So if the difference between electronegative between these two atoms are 0 and 0.4, it's most likely going to be a pure covalent bond, meaning that since their electronegativities are about the same, they're going to not really fight for the electrons. Now, if their electronegativities are very different, then what will happen is that they're going to share it unevenly. So oxygen is usually the one that's the electronegative one compared to hydrogen, so it's going to pull the electrons closer to that. Then, if you have a really big difference, so if you have a metal and non-metal, so you have something on the left side and something on the right side, instead of sharing, they're just going to give it up. So since, like I said, lithium, sodium, potassium, they all really want to get rid of their electrons, and they don't really even want to share. They're like, hey, just take it. I have a full octet. And then fluorine, chlorine, bromine, same thing. Instead of sharing one, they rather just take it. So if it's something between these two, let's say sodium chloride, which is our salt, it will be Na plus and Cl, 1, 2, 3, 4, 5, 6, 7, 8 minus, and they're going to attract each other like that. So there's no bond as in like they're sharing electrons. They're just bonded because one's a positive charge and one is a negative charge. So hopefully that makes sense, how Bohr's model helps us understand shells. And with shells, we only care about the outermost shell, which then we have Lewis structure. Within Lewis structure, we can understand kind of trends in the periodic table where this is more electronegative, less electronegative. And because it's more electronegative, it's going to react differently when it's paired up with somebody that's less or the same. So if they're the same, it's going to be covalent bond. If they're very different, it's going to be ionic bond.